Waves are powerful and important to study. Earthquake waves can cause cities to crumble, and the waves on a beach turn rock into fine sand. Understanding waves is definitely important because they're everywhere in nature, but you might not have known that they're also important for our own survival. Transverse waves are waves where the vibration is at 90 degrees to the direction the wave is moving. That might be hard to picture, which is why slinkies are amazing, or at least one of the reasons. A transverse wave is what you get when you move a slinky from side to side on a table. The other type of wave is called a longitudinal wave. A longitudinal wave is a wave where the vibration is parallel to the direction the wave is moving. That's what you get if you push a slinky along its length, sending a pulse down it. It looks something like this. There are various features we can label on a transverse wave as shown here. A crest or peak of a wave is one of the topmost parts as high as the wave goes. A trough is the lowest part, as low as the wave goes. The amplitude of a wave is the vertical distance between the center line and a peak, or the center line and a trough. This should normally be exactly the same distance. Last of all is a wavelength. A wavelength is the distance from two similar parts of a wave, from a peak to the next peak, or from a trough to the next trough. It is the length of one full wave, one full oscillation. Whenever you measure it, the number should come out the same. The measurement of wavelength we just discussed assumes you are looking at a graph of x plotted against y, like taking a photo of an actual wave at a moment in time. But sometimes, waves are graphed with time on the x-axis, showing how the position of a particular part of the slinky moves as time progresses. On a graph like this, the exact same distance we identified as a wavelength becomes a length of time, measured in seconds. In that case, the peak-to-peak or trough-to-trough measurement is the time period. The time period of a wave is the time it takes for one full wave to pass a particular point. This is yet another feature or part of a transverse wave, and it is important not to forget. Most waves in the electromagnetic spectrum are transverse waves: light, infrared, ultraviolet, radio waves, microwaves, X-rays, and gamma rays. These are all examples of transverse waves. Most kinds of seismic waves, earthquake, are also transverse. Although the first wave you feel when an earthquake hits, called the primary wave or P wave, is longitudinal, everything that happens after that initial hit is transverse. The secondary wave, S wave, is transverse, as are the surface waves and ripples that follow. These transverse earthquake waves all cause much more damage than the longitudinal P wave. If you imagine the slinky as the surface of the earth with buildings on top of it, you might be able to see why. Although sound turns out to be a longitudinal wave, the vibrations of guitar strings contain transverse waves running along them. In fact, they contain multiple transverse waves that interfere with each other to produce a continuous sound. Transverse waves are waves where the vibration is at right angles, 90 degrees, to the direction of motion. On such a wave, we can label lots of features including peaks, troughs, amplitudes, and wavelengths. Examples of transverse waves include every part of the electromagnetic spectrum. Every earthquake wave except P waves, the waves at a beach, and the waves running along a guitar string.